Hey guys, welcome back. So, this is a pretty important lesson for what we've been talking about. One of your goals is to find an alien world, find that habitable alien world. Well, if it's not a terrestrial world, it's not going to be a habitable world. And we think terrestrial worlds are much less common than gas giants and ice giants. The universe seems to want to make gas giants. This seems to be the normal type of planet because they're mostly hydrogen. The star is mostly hydrogen. You generally only get a terrestrial world when the planet is too close to the star for hydrogen ices, and things like that to condense out of that original solar nebula the star system formed from. So you only get terrestrials when it's too hot to make a gas giant. The universe wants to make a gas giant, but we need terrestrials. If we're going to find that alien world, then we've got to find that terrestrial planet. So, in order to find the terrestrial planet, we need to find out the density. The density tells us what is the planet made out of. If the density is going to be really high, somewhere between, maybe 3 and 8, then it's going to be made out of rocks and metals. Terrestrial world that rocks. If if it's around 1, so somewhere between maybe 1 and 3, then it's going to be mostly made out of ice. Ice has a density of 1. And so that's going to be an ice giant like Uranus and Neptune. If it's less than 1, then it's probably going to be mostly made out of gas, and so it's going to be a gas giant like Jupiter and Saturn. So by determining the density, I can figure out what kind of planet it is that we're talking about here. So that's going to be a real important thing. However, this brings together almost everything that we've done this semester into this one calculation. So you really need to understand the previous steps to be able to determine the density, but it's so important to be able to do. So we're going to walk you through all the steps. If you need to review conversions that we did earlier in the week, go ahead and do that. Take a look and make sure that you're good to go for that before you move on. All right, let's get started. All right, so before we get started, we kind of need to know what density is. Density is a measure of how compact something is. You probably heard the old thing about which weighs more, a pound of lead or a pound of feathers. Well, they weigh exactly the same, right? They both weigh a pound. However, that pound of lead is going to be much more compact than that pound of feathers that might fill a room. So that we say that lead then is more dense. It's more compact. It's got more mass in a smaller volume than that pound of feathers. So density then measures mass per unit volume. Basically, that means if I have 1 cubic centimeter, how much mass is inside that 1 cubic centimeter? 1 cubic centimeter is about the size of a sugar cube, if you've ever seen one of those. So gives us a really good measurement for comparing planets. If you're looking at your results, and here's something really important that's worth writing down, your density of your planet should be somewhere between 0.01 and 9. If you're getting something outside of that range, you've done something wrong. Go back and fix it. Use that reality check. You better get something between 0.01 and 9. It's pretty rare to have something up to 9, but it could happen. All right. So we measure its units of density are grams per cubic centimeter. And think about it, that makes sense. Just exactly what it says. I've got a cubic centimeter of the material. How much mass is in there? How many grams are in that 1 cubic centimeter of material? And then, if I've got a planet though, and I've got a whole bunch of those cubes, it still works out to be the same number. If I take any one cube, this 1 cubic centimeter, it's going to have that many grams. Okay. Well, since we need to find the grams, we need to find the mass. And if we're going to find the volume, then we're going to need to find the radius. And you may remember this from high school, but the volume of a sphere you can find if you know the radius. It's pi r cubed, right? Related to pi r cubed. We'll get that number in there. So which detection, let's think back to the methods that we've used before. Which method, transit or Doppler method, do I use to find the planet mass? And which one do I use to find the planet radius? Pause the video and think about it. Fill out both of those on your class notes. Okay, so when we're finding the planet mass then, what are we using? We're going to use the Doppler method. So we're finding that velocity, right? Remember that I also need to know the distance of the planet from the star, and I need to know the mass of the star to be able to do that. If I'm going to find the planet radius, what am I doing? Now I'm using the transit method. That's the one with the dips on the light curve. So the bigger the dip, the greater the size of the planet, the radius of the planet. So I use the transit method for that. So both of these both of our tools give us values in relation to Earth. So the Doppler method is going to give us Earth masses. The planet radius is going to give us Earth radii. But that's not what I need for density, remember? I need the mass not in Earth masses, but I need it in grams. However, we did this last lesson. We converted from Earth masses to grams. So you already know how to get this in the form. We can do something similar to convert our Earth radius into centimeters, but remember that that's the radius. So I've got one more tiny little step. I need to use that radius in centimeters to figure out the volume in cubic centimeters. We'll go through all these steps. So density is in grams per centimeter. So we're going to convert both of these to grams and centimeters. And those conversion factors are on your equation sheet. So let's do a sample. And you can follow along in your workbook, in your class notes here. Let's say that I've got a planet mass, and I've found using the Doppler method that the mass of that planet is 5 Earth masses. And then using the transit method, I figured out that its radius is 1.71 Earth radii. So there are 4 steps that we're going to follow to figure out the density of the planet. I'm going to be doing conversions, and remember the conversion also has 4 steps. So there's a lot of steps that go into this. This is why automating this in a spreadsheet is a good idea. But don't even try to do it in the spreadsheet until you understand how to do it on the calculator. The odds of you putting a bug in your spreadsheet are pretty high. All right, so step 1, we're going to convert the mass from ME to grams, exactly like we did in the last lesson. Then I'm going to use the same technique, and I'm going to convert the radius from Earth radii to centimeters. I'm going to calculate the volume from this Earth radius, that 4/3 pi r cubed. And then once I know the volume and the mass in grams, you just divide the mass in grams divided by the volume, and I'll get the density. I'm going to warn you, where a lot of students mess up is they divide the mass in grams by the radius in centimeters. Nope. Step 2 is just an intermediate step. What you want is 1 divided by 3. Step 1 divided by step 3. Make a note to yourself so that you don't make that mistake, because that's pretty frustrating to be doing all this work and you're going, Kilo, I know I'm doing it right, but it's telling me that I'm wrong. Well, you are wrong because you didn't divide by the correct steps. All right, so let's go through this. So step 1 then, let's convert the mass to grams. Challenge yourself. Pause the video and see if you can do that. If you don't remember how to do the conversion, go back to the previous conversions lecture and use the worksheet. Use the class notes. It takes you step by step through it. So pause the video and figure out the mass in grams. Convert the mass from ME to grams. Pause the video now. Okay, have you got it? All right. So here's my conversion factors. Those are found on the equation sheet. So 1 Earth mass is 5.97 E27 grams. So if I want to know the number of grams, then here's how I set it up. Remember, what I want to convert times a fraction bar. I want the MEs to cancel, so I'm going to put the MEs in the bottom. I'm going to put the grams in the top. The 1 is glued to the ME. The 5.97 E27 is glued to the grams. Last step, multiply by everything in the top, divide by everything in the bottom, and you should get 2.985 E28. So to 3 significant digits, 2.99 E28. If you need to type something in Smart Sparrow, that's fine. But let me give you a tip here. You want your final answer to be 3 significant digits. So while you're doing the intermediate steps, keep 4 significant digits. That way you don't lose any precision when you finally round to that last final number. So for these intermediate steps, I would keep 4 significant digits instead of our normal 3. At the end, you'll round it to 3 significant digits, just like we've always done. All right, so 2.985 E28 grams. That's my planet mass in grams. Does that make sense? Well, 1 paperclip is a gram. It's going to take a whole lot of paperclips to make something that's 5 times the size of the Earth, and this is a really big number. Probably good. All right, step 2, we're going to convert the radius from RE to centimeters. Conversion factor is down there at the bottom. I want you to pause the video, work it out. Okay, you got it? It's going to be set up exactly the same way using our normal steps, and you should get 1.71 RE. Converting that, 1.71 RE, we're going to convert that, and so 1.71 times the fraction bar, here's my conversion. When I multiply that out, you should be getting 1.089 e to the 9, E9 centimeters. If you're not getting that, pause the video, maybe go back, take a look at what you've done in conversions, or just come by Live Help and we can go through it. Are we done? No. We never, ever, ever just divide these two numbers. That's not going to work. Instead, I need to first find the volume. That's step 3. So here's the formula for the volume. If you don't remember it from high school, that's 4/3 pi r cubed. This needs to already be in centimeters. I have had students who happily work out step 2. They'll work out what it is in centimeters, and then they'll take the 1.71 and they'll put it in this formula. Well, why did we bother working out in centimeters first, right? This number goes in for RP. This is the radius of the planet in centimeters. That's what has to go in here. All right, so pause the video, work that out. Let's see what you get. All right, so my volume is 4/3 times pi. If you don't have a pi button on your calculator, you can use 3.14, that's fine. And then times 1.089 E9, whole thing cubed. In most calculators, you don't actually have to put that in parentheses, but it's not wrong to do so. It's up to you. And then when you work that out, you should get that it is 5.414 E27 cubic centimeters. Don't forget that E27. That's real important. There's a big difference between 5 with 27 zeros and just a 5. All right. So now we've got our mass and our volume. I don't need this planet radius in centimeters anymore. Don't use it. To find the density, the hard part's done. I'm just going to divide these. Here's a quick reality check. Your E that I was stressing should be the same, roughly on the same order of magnitude. So these should be pretty close, E27 and E28, that's probably going to work. If I got E9 and E28, that's not going to work for sure. Remember that your final answer needs to come out between 0.01 and about 9, somewhere in there. All right, so go ahead and work it out. Calculate the density, divide by the mass in grams, divided by the volume in centimeters cubed. Pause the video, see what you get. All right, so density is the mass divided by the volume. We're filling in our numbers here. See that I've got the 28 and the 27, so this number divide by this number, and you should get a density of about 5.51. Is that in between 0.01 and 8? Yeah, probably I'm good. So now that we've got the density then, what is the planet made out of? And this is something you're going to be working with quite a lot in the lab for this lesson. So if gas tends to have a density of around 0.5, ice is around 1, rock is around 3, metal is around 8. It's almost always going to be composed of more than one of these things. And the simplest thing is if it's only composed of 2. That's a clue for the lab. The simplest way to represent it is to assume there's just 2. Well, we got 5.51. So that means it's between 3 and 8. It's going to be somewhere in here. So that tells me that my planet must be made out of rocks and metals. Do you see how that works? Now in the lab, this is going to be a bit challenging for you. I'm going to warn you. You're going to have to adjust the amount of rock and metal until it matches both the size, the mass, and the density so that you're getting the density. So some tips for that is get it close. Use the sliders to get it in the ballpark. And then if you need to increase the density, add metal and subtract rock in this case. If you need to decrease the density, add rock and subtract metal so that you can keep the size basically the same. Same thing if it works out between 1 and 3, you're going to use water, ice, and rock. If it's between 0.5 and 1, you're going to use gas and water ice from that. All right? It's going to be a challenge. It's going to take you a little bit longer for this one. This is one where a lot of students get frustrated because it really is just kind of play with it until you get it. There's no mathematical way to get it. And for all you guys saying, oh, I hate math, you actually probably love the math because it takes you straight there. Here, you're just going to have to play with it, work with the mixing. If you've got problems with that, you definitely probably want to do this lab in Live Help with me because I can give you some tips that'll get you there a lot faster. So plan on coming to Live Help and doing this one with me. All right. So this is going to give our terrestrials then our rocks and metals. Our ice giants are going to be made of mostly ice, and our gas giants, of course, are mostly gas. All right. So you're going to get some practice using the worksheet. Do that first. Definitely do that before you try to do the lab. I strongly recommend it because the lab is challenging enough if you're also having trouble finding the density in the first place. All right. So make sure that you've got that. And if you're struggling with that before you get to the lab, come see me. And then maybe while you're there, let's just go ahead and do the lab. And we'll do it together. Okay, guys, so now you know how to find the density of the planet, and that tells you directly is it a terrestrial world, an ice giant, or a gas giant. You're going to have to find some gas giants and ice giants as part of your project, but there's dozens out there, hundreds out there. It's really not going to be a problem to find those. That terrestrial world is the magic one that you're looking for. When you're doing your final project, you're going to say, oh, look, there's a planet. You're going to work out the density, and if it is a gas giant or ice giant, you say, you're dead to me, and you're going to move on because there's no chance that that is your habitable world. On the other hand, if you found your terrestrial world, now it's time to get excited because now you might have actually found your alien world. We don't know yet. We still have to find out if it's habitable. And we've got to talk about in the next sections, what does it mean for a world to be habitable? What does it mean for it to be capable of supporting life? But from the beginning, you have to have a terrestrial planet or there is no chance that that's going to be able to support life. All right? We'll see you next time.